Welcome back to Machine Learning Guide. I'm your host, Tyler Ranelli. MLG teaches the fundamentals of machine learning and artificial intelligence. It covers intuition, models, math, languages, frameworks, and more. Where your other machine learning resources provide the trees, I provide the forest. Visual is the best primary learning modality, but audio is a great supplement during exercise, commute, and chores. Consider MLG your syllabus with highly curated resources for each episode's details at ocdevel.com/MLG. I'm also starting a new podcast which could use your support. It's called Lefnir's Life Hacks and teaches productivity-focused tips and tricks, some which could prove beneficial in your machine learning education journey. Find that at ocdevel.com/LLH. You're listening to Machine Learning Applied, and in this episode, we're going to talk about machine learning hosting solutions out there with a special emphasis on serverless technology. In the last Machine Learning Applied episode, we talked about various tech stack solutions, especially for serverless solutions for hosting your server. The Amplify stack in particular uses behind the hood AWS Lambda, and AWS Lambda is a very popular solution for serverless architectures. AWS Lambda lets you write a single code function, whether it's Node.js or Python, and then that function, in conjunction with AWS API Gateway, will be exposed as a REST endpoint that your client can call. Very powerful and saves you a lot of time and heartache. Now, we want to achieve this level of functionality when deploying our machine learning models. So in this episode, when I'm talking about machine learning deployment solutions, I want to push towards as much of a serverless solution for deploying your machine learning models as possible. Now, I want to preface by saying my own experience in machine learning hosting is slightly limited, and in my experience trying to find the best serverless machine learning hosting technology available, I've found that the providers are somewhat limited. And this makes sense. We've been deploying regular servers, app servers, using FastAPI and Node.js for a very long time. And so hosting providers like AWS and GCP have had a lot of time to sit with this problem in order to come up with solutions like AWS Lambda, where machine learning is a more recently popular technology. And so they haven't had as much time to really perfect this space. So you will find that even within a single cloud hosting provider like AWS, there are competing machine learning hosting solutions, and it's not clear when you might want to use one solution over another, and that any one given solution doesn't really solve all the problems you need. So it's an evolving space, it's a nascent field, and things are only going to get better. All that's to say that this episode is going to be due for a refresh before too long, so expect to follow up on this episode in the future. Now let's start with types of hosted machine learning scenarios. The first type is if you want to train your model in the cloud. Now, training is the most expensive component of the machine learning story. It's the most time and computation expensive part of the end-to-end machine learning story. What you'll usually do is you'll train a model, and that includes hyperparameter optimization of the model, so not just the training phase, but cross-validating against validation error and checking the test error and tweaking hyperparameters, etc. This can span multiple days for a single model, depending on the training set. And then later, you'll end up using that model for inference, and inference is the cheap part. Usually, inference can happen in any number of seconds or milliseconds. So it's time cheap, and it's also computationally cheap. So these two phases of the machine learning pipeline are separate and handled differently. The training phase is extremely expensive. The inference phase is cheap. So you'll want to use different technology options for these different phases of the machine learning lifecycle. In the training phase, you don't have to do it in the cloud. You could do it on your desktop. You could train your model on a custom-built GPU-heavy desktop, which is what I typically do. Save the result of the trained machine learning model. This is what we call artifacts. So the artifacts are the result of a saved machine learning model. If you've got a TensorFlow machine learning model, you'll save it in the TensorFlow format. If you've got another model, let's say XGBoost or something else, you might save it via the Python joblib library. to a pickle file or something like that. So the exported saved dump of your machine learning model is what we call an artifact. And then you will take that artifact and deploy it to wherever you're going to be hosting the inference part of your machine learning lifecycle. So that's one option, is that you could do the training on your desktop. But another option is that you can cloud host the training phase of your machine learning model. And there are a number of cloud hosting solutions for the training phase. And this is especially valuable if the training phase may take multiple machines. Let's say your desktop just doesn't cut it. It's not enough. Even if you have a very beefy, powerful desktop, it's still not enough. You may need to parallelize the training phase of your machine learning. Then you might want to consider a cloud hosting solution. And of course, I always mention there's 3 popular cloud hosting solution providers out there. GCP, Google Cloud Platform, that is Google's web hosting offerings. AWS, or Amazon Web Services, that's Amazon's web hosting solutions. And Microsoft Azure, Azure. And of course, that's by Microsoft. So Microsoft, Amazon, and Google. Now, in the past, I recommended that you consider Google primarily. And the reason I said this is a long time ago in one of my early machine learning guide episodes. The reason I said this is that Google really is the king of machine learning. They really are. I mean, their primary business model being ads, AdWords and AdSense, is very, very machine learning heavy. And their secondary business model, which is driven by their primary business model, is search. And search, of course, is machine learning heavy, using actually these days primarily BERT technologies. Google puts out just white papers hand over fist. Google is one of the leading, absolute cutting edge participants and contributors to the research space of machine learning. And so necessarily they would have fantastic machine learning backend services and solutions. And they do. GCP is absolutely fantastic tech. And they offer things that other cloud providers don't offer, something like the TPUs, tensor processing units, as opposed to GPUs and CPUs, which streamline your TensorFlow code immensely, makes your TensorFlow, both training and inference, much faster than what you can get on GPUs and CPUs. So GCP is a fantastic solution. I highly recommend it. But since I've made that recommendation in the past, I never did make the switch myself to Google. I've always been a bit of an AWS guy. And it's just that AWS, they just innovate so fast on their cloud hosting solutions. And they're just so tried and true that I've found working with AWS to be easier than working with GCP. And most of the projects that I get involved with end up using AWS. And most of the resources I find out there, tutorials and videos on cloud hosting, end up being on AWS. So it's just that over time I found that AWS provided the least inertia for me as a developer. And so you might find that to be the case for you as well. So I would recommend AWS. Consider AWS first before GCP or Microsoft Azure. But if you take this seriously, then of course consider all 3 options. Weigh the price of the services that you're going to be using, especially with the machine learning hosting services, because GPU hosting is extremely expensive, and the price difference between the 3 services is very drastic. But there's no clear winner to say that one is cheaper than the other. It just depends on the services you use, whether it's this type of GPU or that type of Kubernetes orchestration, etc. So for the rest of this episode, I'm just going to be focusing on AWS for my examples. But bear in mind that all 3 cloud providers offer equivalent services for almost everything I'm going to be discussing in this episode. So for example, we're going to be talking about SageMaker right now. And SageMaker is an AWS service, but Google offers an equivalent service called CloudML. And then I'm sure Microsoft Azure offers an equivalent service as well. AWS SageMaker is a service for training, monitoring, and deploying your machine learning models. And AWS SageMaker is probably the most well-known of the cloud-hosted machine learning solutions out there. And the reason being that it is the most end-to-end solution out there. It provides the training component, the everything in between component, including monitoring your model's trainings and outputting the artifacts, and then exporting those artifacts into a deployed API via REST endpoints. Now we're talking about the training phase here, so what you might do is use SageMaker to train your model on, And you can do that either through the SageMaker API or console, or SageMaker allows you to spin up a notebook, a Jupyter notebook, where you can write your code and interact with the code in a web browser on the deployed SageMaker instance that you're using, and then train your model directly from within the Jupyter notebook, and then you can dump the artifacts of your trained model at the end of your session. And then you can close that Jupyter notebook and you can deploy those artifacts to a REST endpoint, which we'll talk about that in a bit. But one of the big benefits that SageMaker offers you in training your model is sort of this auto-scaling and parallelization if necessary, if you need lots of compute to train your model. And another benefit that SageMaker offers is monitoring of your model's training process. So something SageMaker adds that the other AWS machine learning solutions doesn't provide is a lot of insights into the process of your model. This might be accuracy metrics, error, actual error metrics, like if you're throwing errors and things like this, compute resource utilization and all these things. So it gives you a lot of tooling in the console, in the AWS web console, to monitor the training process of your machine learning model on top of whatever tooling, whatever framework you're using provides. So for example, if you're training a TensorFlow model, well, TensorFlow has this package called TensorBoard, and TensorBoard gives you visual insights into the architecture of your neural network. And that might include things like the distribution of any one neuron, the distribution of the weights, so you can tell whether things are going awry, whether they're overfitting or underfitting, whether you're getting vanishing or exploding gradients in the training process, etc. So that's TensorBoard. Well, that's the type of tooling you might expect that SageMaker provides for the training process and monitoring of your machine learning model. So SageMaker is very robust and powerful, and it's an end-to-end solution. And like I said, what you do then is you, at the very end of your notebook or however you want to interface with SageMaker, you're able to export your model, your saved model's artifacts, and then you can use those artifacts to deploy REST endpoints for your machine learning model for inference. So you've done the training process. Maybe let's say it takes a half hour or an hour. You've got a trained model. And now you want to use that model on the web. You want your app server, which exists on either AWS Lambda, or it may exist as a Docker container on ECS Fargate. And that app server is going to interact with your machine learning model in order to provide results to your end user on the client. Well, you don't want to deploy your machine learning model on the Fargate instance because that instance is going to always be on, and you don't want to attach an expensive GPU to it. You want your app server to handle what it handles best, and that's running a web server. So you leave it alone, and you deploy your SageMaker's saved artifacts model to a REST endpoint through SageMaker, and your app server now can interact with your SageMaker model's REST endpoints in order to retrieve results via inference of the machine learning model. So SageMaker creates a web API for your model. That's special. It does a lot of the heavy lifting for you in order that you can host a model without actually spinning up an EC2 instance, setting up TensorFlow and PyTorch, creating a web API on that instance to expose the model's inference API and all these things. So SageMaker is end-to-end. It does everything for you. If you want a one-stop shop hosted machine learning solution, then SageMaker is your guy. Now, why might you not want to use SageMaker? That seems to be just the conclusion to this podcast episode. Let's stop here and just say SageMaker is the king and we're done. Well, there's a couple things that are a bummer about SageMaker. The first is it's very expensive. So it's going to be using a GPU instance, EC2 instance with a GPU attached. A very common one that people use is called a P2.X large. That's one of the lower EC2 instances that support a lot of the modern machine learning frameworks, but it's still quite expensive. If you were to host your own EC2 instance on a P2X large and write up your own code to deliver your machine learning model's inference capabilities. You write your own REST endpoints on that EC2 instance, let's say using Fast API, for example. You would have a couple benefits. One is you'd have a lot more control. Two is that you can use spot instances if you want, although you'd have to take care that those instances might get shut down if the price of these spot instances goes above your max price bid. So that's one solution, is host your own on an EC2 instance, and it would have this flat cost if you're not using spot instances. Well, that cost on SageMaker is 40% more. So for the P2 XLarge instance manually done via EC2, you're paying 40% more to replicate that on SageMaker. Now, granted, SageMaker provides all these bells and whistles, these benefits, and saves you a lot of time, so it's very likely worth it. It's almost never a good idea to custom host your own model on EC2. You're going to want to use one of these solutions available on AWS instead. You want to get as serverless as you can. We're trying to move away from EC2 as much as possible over time. It'll just save you time, heartache, and unnecessary boilerplate coding. So we don't want to use the EC2 model, but going with the SageMaker route, we end up paying a 40% premium. That's a big bummer. Another bummer is that whatever SageMaker deploys is always on. Always on. Now, if your machine learning project, your app, which uses machine learning on the back end by way of SageMaker, for example, is constantly being hit and has a huge user base, and users are constantly running the machine learning inference capabilities of your machine learning model, that's fine. You always want it on anyway. And what SageMaker provides for you out of the box is auto scaling of your machine learning model's inference. Auto scaling, that's very, very important. That's another benefit of using SageMaker instead of EC2. Auto scaling, auto deployment, auto provisioning of server architecture and instances, blah, blah, blah. So if you have an app that has machine learning and that machine learning is in constant use, then it is very unlikely that you need to take that server down ever anyway. So an always-on server via SageMaker is A-OK. That's exactly what you want. But if you're a startup and you don't have a lot of users, like I don't with Nothi doesn't have enough users currently using the machine learning capabilities of Nothi that would warrant the expense of keeping a SageMaker deployed model always available, then I would be paying just excess cost out the nose. I'd be paying a 40% increase on the cost of whatever EC2 instances is deploying. And B, I'd be paying for it to always be on, even if it's only being used some of the time. Okay, so that covers SageMaker. Again, SageMaker is an end-to-end machine learning training and deployment solution with all sorts of bells and whistles, including monitoring the training phase of your machine learning model and deployment of a REST API for inference provided by your machine learning model at scale, with auto provisioning, auto this, auto that. Everything is just handled for you, but with a premium. That premium being 40% additional cost of the EC2 instance you're going to be using and the model always being on. As long as you're okay with that premium, then the solution is great for you. And again, GCP has an equivalent solution to SageMaker. It's called Google Cloud ML. And Microsoft Azure, I'm sure, has an equivalent solution to SageMaker. I don't know what it is. I'm very unfamiliar with Azure's offerings, unfortunately. Now, there's another concept called elastic inference provided by AWS. An elastic inference allows you to attach as much GPU compute power as you want to whatever EC2 instance that you need without using a full GPU instance. Now, that's a little bit confusing. The idea goes like this. The P2 XLarge EC2 instance uses I believe it's the K80 GPU. So it attaches a K80 GPU with this much RAM and this much compute power. Well, especially at inference, in the inference phase, when you've deployed your model to the cloud at a REST endpoint and you're making predictions, that GPU is going to go wildly underutilized, even when you have a lot of users and the machine learning model is constantly in use. Even then, because inference is so cheap, you're still very likely to be underutilizing your GPU, and therefore you're going to be paying for more than you should be paying for. So what cloud inference does is it allows you to attach a number to whatever EC2 instance you might be using. A number of GPU compute power and RAM without actually specifying which GPU you're going to be using. And that allows you a little bit more flexibility to drive down the costs of your deployed machine learning model. You're less likely to use this inference API at training time. Actually, that's kind of the point. That's why it's called the elastic inference API. You don't use it at training time because training time is going to be probably using your GPU to the max. But at inference time, it's very unlikely to be using the full GPU. And so it's better and more cost effective to use this AWS elastic inference system rather than a full-fledged GPU EC2 instance. So rather than using a P2X large EC2 instance in this example where we're deploying our own model on EC2, which is never suggested, rather than using a P2X large instance, you might use whatever kind of instance you want, including just the standard instances with normal CPU and RAM, and then attach some amount of GPU compute and GPU RAM, some small amount that you think you might be utilizing, and then that way you'll save costs. And this elastic inference solution is available to SageMaker, actually. So even though the SageMaker deployment of your model is a 40% cost on whatever instance you're using and is always up, you can still shave some cost off, quite a substantial amount of cost, by not using one of the GPU instances and instead using the elastic inference API. So that's one way to get a cost savings on SageMaker. It's compatible with the elastic inference API. Okay, so that's SageMaker. SageMaker is the end-to-end training and deployment. Now let's talk about training only and deployment only offerings. The traditional training only offering is something called AWS Batch. AWS Batch lets you run a Docker container to completion, and then it dies, and then it goes down. And then what kicks off this batch process? Well, you would either call it through a CLI call or trigger it manually in the AWS console, or you can use the Python Boto 3 library on your app server to trigger a batch job. So what batch is intended to do is run heavy jobs. It's not just for machine learning. AWS Batch is primarily intended for any batch job, any heavy job that is Docker containerized, which is intended to run once and then die. So you would kick off an AWS batch job, and that batch job might be, for example, training a machine learning model. That's a prime use case of AWS Batch. Now, Batch doesn't offer all the tooling that SageMaker offers on monitoring your training process and all those things. And it certainly doesn't offer deployment of a machine learning model to a REST endpoint. But what Batch does offer is a lot of cost savings. So the job dies eventually. So as soon as it's done, it dies. And that means you don't have an EC2 instance always on, racking up costs. And B, you can specify that that batch job should use a spot instance if available. And so what you end up doing is you set up a batch environment. You say, I want it to run on a P2X large. It's going to deploy this Docker container, which is, for example, a machine learning training job. And if available, spin up a spot instance of that P2X large. But if not available, then use a standard P2X large instance. And then that way, if there is a P2X large that's available in spot instance, you'll save a lot of costs, sometimes up to 90%. And if not, it will run in standard mode. If you need the batch job to run immediately, no matter what, alternatively, you could say, always use a spot instance. Don't fall back on a standard instance. And you would do something like that if it's not time sensitive, if it doesn't really matter when that machine learning job runs, just as long as it runs eventually, then you might use a spot instance only batch job. Now, try to think outside the box on how you might use batch, because with the cost savings that batch provides, A, it being a spot instance, B, it not being 40% extra cost, and C, it dies when it's done. Well, check this. I'm using Batch for Nothi's machine learning server. In other words, my Batch server is basically my deployment server, which is not Batch's intended use case. Batch is intended to fire and forget some heavy job. Well, what I do is the app server, the server, when a user comes online, if there's not already a batch server running, then I use the Boto3 library, which is Python's AWS library, Boto3, BOTO3. I use the Boto library to spin up a batch instance, and that runs my inference system. It puts the inference system online. Now, that inference system is running in a batch job inside of a Docker container. And machine learning requests for inference, prediction requests, are sent to that batch job by way of job queue. You might use RabbitMQ or SQS, Amazon SQS. I actually don't use any of those. I have my own handcrafted job queue system by way of Postgres, which I mentioned in the last episode. Postgres is so powerful. It offers a job queuing-like system just due to the nature of some of its capabilities, as well as some pub/sub capabilities. So eventually I'll probably move to a system like RabbitMQ or SQS, but for now this Postgres-only job queuing system is working fantastically. So I send job requests to the batch server from the app server. The batch server runs these machine learning inference jobs like a summarization report or question answering in Nothi or theme generation in Nothi, all these things, returns the results. And then it waits for a while, and if it hasn't received a new job in, let's say, 5 to 15 minutes, it turns itself off with an exit 0, exit parentheses 0 parentheses. And what that exit 0 thing does is it kills the Python process, and a killed process is what batch is looking for in order to take the instance offline. Normally, like I said, the way people use batch as intended is to run a script. Maybe that's a machine learning training script to completion. And at the end of a Python script, at the completion of a Python script, implied is exit 0. So that's the intended use case. But what you could do with batch is run the whole thing in a loop so it never exits until you want it to. And now what do you have? You have a machine learning server. Okay, so it's a little bit of a hack job, and it doesn't offer some of the benefits of SageMaker, but it does offer a substantial cost savings while not requiring the server to be online all the time. Let me tell you what it does not provide, that SageMaker does provide, is auto scaling. So when I get enough users that would warrant more than one machine learning server, then this solution is going to go out the door and I'm going to switch over to SageMaker. This is a temporary solution during the regimen in which I have very few users using the machine learning services. Okay, SageMaker end-to-end, batch for big jobs, and that's a shoo-in for machine learning model training. And batch uses Docker containers. So you're going to Dockerize your machine learning stuff into a container, and then you will run that container's script to completion. And at that point, AWS Batch takes itself offline. Now, as far as I understand, you could probably use Elastic Inference API with Batch. I'm not sure, actually. The way I understand Elastic Inference API is it's sort of this one-size-fits-all replacement for GPU instances if you are primarily using that instance's GPU capabilities for inference, not for training. Something you might need to look into if you want to add more cost savings when using AWS Batch is see if it's compatible with the Elastic Inference API. I don't know. Now, let's pause here real quick. I'm going to mention another solution offered by AWS called EFS, Elastic File System. And EFS lets you attach a file system, a mounted network file system, to any service, whether it's EC2 or AWS Batch or SageMaker or Lambda. And that file system is permanent. So if your AWS Batch container gets taken offline when its script has completed as it's intended to do, whatever files you save, including model saves, saving model artifacts to disk, gets deleted when the AWS Batch container gets taken down. Its file system is ephemeral. It's temporary. It's intended to be deleted on server takedown, and that's normal. If you don't want that, then you will use EFS. EFS is a permanent file system that you can attach to all sorts of different services, and they'll share the file system amongst themselves. They'll all be able to contribute to the same file system. And when those services get taken offline, like AWS Batch coming offline, then that file system will still remain available to you. AWS offers all sorts of different file system solutions, the most obvious of which is called AWS S3. S3 is where you'll store files, usually which are intended to be available to access on the web, for example. But sometimes you want a private file system that's only available to your servers. But you don't really mount an S3 file system. An S3 file system is more like Dropbox or Google Drive. It's something where you put stuff over there, and maybe sometimes you'll pull stuff out of, but it's not intended to be a read-write file system that you're consistently accessing from an operating system. For that, instead, you'll use EFS. So with these solutions that I've discussed so far, SageMaker and Batch, you're almost certainly going to want to combine them with EFS because you're going to be saving your model artifacts. You're going to be saving various, training information, training data. You want a large spreadsheet or a SQL dump to be one-time save, consistently available on operating system startup, available as a mounted file system, and so on. Another reason you would use EFS, something I use in Nothi, is that a lot of these models, pre-trained models that you're going to be using in your project, like the Hugging Face Transformers models. Well, Hugging Face Transformers, you would install the package via pip in the Docker container, in the Docker file, pip install Hugging Face Transformers. But the models that are loaded by that package, the models themselves, which are pre-trained models with PyTorch weights and TensorFlow weights, are downloaded from the internet, and they're very large. They can be in the order of 4 gigabytes or more per model. So 4 gigabytes per model. In Nothi, I have a summarization model, a question-answer model, a sentiment analysis model, and more. So let's say that I'm dealing with 4 gigabytes per. Well, I don't want to re-download each model every time I provision a batch instance. So batch, every time it comes online, it has to re-provision the instance based on the Docker file. You want to keep your Docker file as minimal as possible, so it has to download as little as possible. And the only way you can achieve that is that you have the big stuff, like Hugging Face Transformers models, for example, pre-downloaded onto an EFS drive, not downloaded by way of the Docker file, and that EFS drive is mounted to the batch container. Okay, SageMaker for end-to-end, Batch for big jobs which run to completion then die, but it doesn't have to be that way. You can run some tricks where it's an infinite loop and it exits when you want to. And EFS to ensure that persistent files are stored between ups and downs of your servers. Now, here's where things get a little bit tricky because SageMaker, I think, is an obvious solution for people with deep pockets and a big system that just needs to work and always be available. But what about people like us and my project Nothi, which doesn't have deep pockets, nor a lot of users consistently using the machine learning capabilities? That batch system that I just described to you doesn't really work fantastically. It works for now because I don't need to scale this thing. But eventually, I want a solution that maybe saves cost by comparison to SageMaker, but ideally provides some of the capabilities of SageMaker. So for example, a auto-scaling inference REST endpoint, but also allows that endpoint to scale to 0. In other words, when someone's not using the machine learning capabilities, whatever solution I use ideally can turn itself off so it's not incurring costs while no one's using it. Well, I did mention in the last episode the solution AWS Lambda. Lambda lets you write Python functions or Node functions in order to deploy a single function as a REST endpoint in conjunction with API Gateway, another AWS service. The problem with Lambda for machine learning is that Lambdas do not have GPU access. Even they don't have the Elastic Inference API compatibility. You can't use Elastic Inference API on AWS Lambda. In other words, you cannot use a GPU with Lambda. It is impossible. As far as I know, if I'm wrong, please send me a message and correct me, because this, to me, would be the ideal scenario, is if we could get GPU access on Lambda to deploy our own machine learning inference endpoints. The cool thing about Lambda is, as long as you're not computing, as long as a Lambda function is not being called, you are not being charged. That's an immense benefit. To me, that's the real benefit of Lambda. Unlike EC2, if you have your own EC2 service, or even if you're using ECS and Fargate, and a deployed Docker container, that service is always on, and so you're constantly being charged. Lambda is not always on. It spins itself up in real time when it's being requested from a client. So it comes online as needed in order to do its job and then goes offline. That's wonderful. That is absolutely wonderful. Now, traditionally, the compute cost of any one Lambda endpoint is pretty low anyway, so that's not a huge deal. The real benefit of Lambda is that it auto-scales and it auto-provisions all the server architecture and all this stuff. The real cost and time savings benefit of Lambda is all the stuff it does for you, the orchestration, the scaling, the endpoint creation, and all that stuff. But if you could potentially have Lambda attached to a GPU such that it would only run a machine learning model inference when called and then taken offline, you could save an immense amount of money and get most of the functionality you desire that you get from SageMaker's deployments. But you can't, unfortunately. You can't use a GPU on Lambda. However, some people are still using Lambda nonetheless for their machine learning deployments. And the way they do this is, first off, remember that I said that the cost of inference of a machine learning model is substantially less than the cost of training. Well, with this in mind, some people have found that maybe they don't actually need a GPU at inference time. Maybe their model is quick enough, not quite so compute intensive as to necessitate a GPU at inference time, not at training time. You always need a GPU at training time. But at inference time, maybe you don't need a GPU. And so they deploy their machine learning models to Lambda, not Batch, not SageMaker. They deploy it to Lambda. And again, they have to use EFS attached to Lambda so that your Lambda function has access to the file system, and then that file system has the saved model artifacts, let's say a TensorFlow model or a PyTorch model or a XGBoost joblib pickled file, etc. So the Lambda function loads up a saved model from EFS disk and uses it simply for inference. And some companies have found that even though, yes, there is a reduced performance of the model's compute power on Lambda, they have found that nonetheless, it is sufficient for their needs. It's enough for them to use the minimal Lambda resources to run inference on a machine learning model. What they find, and some of the things I've read, is they say, look, a small amount of CPU and a small amount of RAM is not that much, especially when we're running inference on deep learning models. But the whole point of Lambda is that it auto-scales. That's the real big benefit of Lambda. So if you have a single function, you have 100 users hitting that machine learning model at once, well, those 100 requests are 100 different Lambda calls. And therefore, each function call is loading up its own model into memory and running inference and sending back the results. So the parallelization capabilities of AWS Lambda compensates for the lack of GPU availability when running inference on these models. So if you're listening to this episode and you want to cut costs, SageMaker's too expensive, or you don't want to have something online all the time, then what I would recommend you do is consider whether or not you could use AWS Lambda to host your model for inference. In other words, think about whether or not your model can be loaded into RAM. The minimal amount of RAM that Lambda provides, I think the max RAM a Lambda function provides is 3 gigabytes, and the max CPU capabilities a Lambda function provides is 2 virtual CPUs. So think about whether that's enough for one inference call. And if it is, use Lambda. Deploy your machine learning model's inference capabilities to Lambda functions. If it's not, then you'll consider some alternatives like Batch or some more stuff that we're going to discuss here in a bit. One more thing about Lambda. If the compute resources provided by Lambda is insufficient to run the inference of the model that you want to deploy, there's one more trick you can try, and this is something I plan to try with Nothi. I want to try moving away from batch. Batch really is not the right solution. I'm not using batch the way it's intended to be used, and that's going to bite me in the butt eventually. Batch is really intended for like training jobs, for example. I'm going to try moving from batch to Lambda, and the way I'm going to do it is the following. There are these tools out there which I will discuss in a future episode. They're considered these optimization tools, machine learning model optimizers. And I'm not talking about an optimizer like Atom or Atagrad. We're not talking about backprop. We're talking about the whole machine learning model, a exported TensorFlow model artifact, or an exported PyTorch model is piped through an optimizer, and out comes a faster model. It's basically like a zipper, like a zip file. It's like a compression algorithm of your machine learning model. It compresses it. It literally compresses it. It does some tricks on the model itself, on the weights and the neurons. It can remove neurons as necessary. It can quantize the types of values that can be represented at any one given neuron. Another thing it can do is reduce what, usually these models have like floating point 32 variable types as the weights. Well, it can downscale from floating point 32 to floating point 16, or even more, floating point 8. It will learn all the tricks of your exported model without reducing the accuracy too much, and then export a substantially minified version of your machine learning model. And now that model can run on CPU. So your previous model, let's say a Hugging Transformers model, for example, a lot of those probably won't work very well on CPU. They probably won't lend well to an AWS Lambda function. But you pipe the model through one of these optimizers, and out comes a minified version of the model, which can be used on AWS Lambda. CPU only, small amount of RAM, A-okay. We lost, let's say, 1%, 2% accuracy, big deal. It's worth the cost savings and the scalability and all that stuff. These optimizers, the most popular out there is called Onyx, ONNYX. Like I said, I'm going to do a dedicated episode on optimizers. They're very valuable, very powerful tools. And another popular one is called OpenVINO. OpenVINO, and that one's by Intel. If I recall correctly, I don't know that OpenVINO is necessarily intended for general purpose model optimization. I think it's intended for optimizing your model to be run on Intel CPU chips. Now, if your AWS Lambda functions are running on Intel CPUs, which I think they are, then, win-win. You're getting what you wanted out of it. But just keep that in mind. I don't think OpenVINO is a general purpose optimizer. I think it's an Intel CPU optimizer. A lot of times OpenVINO is used for things like camera models, computer vision models, which are deployed on small cameras intended to be run at the edge, where that camera only has an Intel chip. It doesn't have a GPU or anything else. And so OpenVINO tends to have a very specific use case. But Onyx is a general use case optimizer, ONNYX. Onyx is a general case optimizer, and it has a lot of other benefits as well. You'll hear about Onyx. If this is the first time you've heard about Onyx, I promise this won't be the last time. Onyx is not just about model optimizing. It's also about model file format generalization. So when you pipe your TensorFlow model through Onyx, and out comes an optimized model, a smaller, faster, leaner model with not too much reduction in accuracy. Another benefit of what just came out of the pipeline is something that can be deployed on all sorts of different architectures. So Onyx is not just about optimization, it's also about compatibility. But we'll talk about that in a future episode. Let's move on from Onyx. So SageMaker, end-to-end solution, all sorts of bells and whistles, all sorts of tooling. Deep pockets, lots of users, go SageMaker. Batch runs a one-off fire and forget, big job. Great idea for model training. Lambda is a bunch of tiny little servers where every client request spins up that function into CPU and RAM and then spins it down. Normally not used for machine learning, but a lot of people have been recently using it for machine learning. The main way they do that is either their model would run just fine for inference purposes on that Lambda instance because inference is cheap. But if inference is still not cheap enough to run on a Lambda function, You can force it to be so by running your machine learning model through Onyx to output a minified version of that model, which now can run cheaply on a Lambda function. And of course, I mentioned EFS, your file system where you store your model artifacts, your saved model dumps. You would want to pipe your model through Onyx first and save it to your EFS file system in advance. And that way your Lambda function calls would load up from EFS the minified models, the optimized models, not the original models. Now, as far as I understand, that about brings us to a conclusion on the AWS machine learning offerings. Like I said, I mean, you could do all this stuff on EC2 yourself manually. You could also do all this on ECS, Elastic Container Services, by using a Docker container, and that will relieve some of the deployment overhead of spinning up manual EC2 instances and such. But I just wouldn't recommend it. It's too expensive and it's too much legwork to write the code which is going to serve up your inference engine and all these things. For machine learning model deployment, I definitely would not recommend running a custom EC2 server. But even at the ECS level, I don't know that I would recommend running a containerized machine learning model on ECS. You could do it, and you could probably get some cost savings, but there might be a little bit more to the programming and the management and making sure that sort of everything works together and scales effectively and stuff. So that covers the machine learning solutions offerings by AWS. And like I said, GCP and Azure have their own equivalents to all of this stuff. But there are third-party providers out there that are competing in this space now. One is called Floyd Hub. I don't know much about them. Another is called Paperspace. They do stuff similar to SageMaker. It's a similar offering to SageMaker where you can train and monitor your machine learning model and then deploy it as a REST endpoint. And they also have an offering similar to AWS Batch, where you run a one-off instance that dies at the end. And these services are very similar to their counterparts. They offer the same types of solutions. For example, their batch equivalent has a cost savings and can use spot instances in a similar way as AWS. Now, why would you use Paperspace if AWS has all this stuff built in? Especially since a lot of us are using AWS already. Wouldn't we want to be using the VPC that we might be hosting our other services on and so on? Well, Paperspace is a lot cheaper than AWS, actually. For some reason, I don't know how they've pulled this off, but they've found a way to make things a little bit cheaper than AWS SageMaker and AWS Batch. I don't know exactly how they pulled it off, but I did experiment with Paperspace some, and I found that they were cheaper than AWS on average. But I still prefer AWS, like I said, because I am using all the other AWS services. And I do want that EFS file system, for example, to be available to other AWS services outside of the machine learning servers I'm running. So I still prefer to stay in AWS rather than Paperspace. Although do look into Paperspace. I believe you can set it up to run inside your AWS architecture, as well as there's a way that you can run Paperspace services on-prem on your own servers in like an on-site server farm, physical servers, and so on. I will say to you, check out Paperspace, but maybe don't get your hopes up too high. I think the AWS offerings are pretty much all you need, but check out Paperspace and see if you like what they've got. Finally, there's one last cloud hosting solution I want to discuss that I'm really excited about, but I don't know enough about yet. And it's called Cortex. Cortex.dev, D-E-V. Cortex.dev. Cortex.dev is an open source cloud hosting setup. It uses your AWS stack. It actually orchestrates the provisioning of the various services in your AWS stack needed to run various machine learning components of a full-fledged architecture. Okay, so let me step back. What you do is you pip install Cortex and you write your traditional machine learning code, TensorFlow, PyTorch, Hugging Face transformers, etc. And at some some point in your code, you'll run inference through your machine learning model, or you will run training on your machine learning model, and you will have it tied into Cortex in one way or another. There will be some flag, I'm kind of like blowing smoke here as I'm trying to wrap my head, because I haven't used Cortex yet, so bear with me as I try to describe what I understand of Cortex. But at some point, there's like sort of a flag that tells you whether you're in dev environment or in production environment. And at the point at which you would call inference on your machine learning model, in the standard way that you would call inference, like model.predict on your TensorFlow model, if this flag is in development mode, then it'll do the normal stuff. It'll run it all on your GPU. But if the flag is in production mode, it will kick off to AWS through the Cortex system. And what Cortex will do is it will auto-provision EC2 instances, spot instances if available, and scale them up and scale them down as necessary. And one thing that they're working on, which is the reason I'm so excited about Cortex, is scale down to 0. In other words, what Cortex does for you is it's basically an open source SageMaker, where it does the end-to-end stuff, training, monitoring, and inference and deployment to REST endpoints. It does all that for you, same as SageMaker, without the added cost. It doesn't incur that 40% extra cost. And in fact, with a reduced cost, because you're able to use the spot instances if available. So it's cheaper than SageMaker. And last but not least, one thing they're working on, which isn't yet released, is scale down to 0. So if you don't have users using the service, you can specify some cooldown period. After 15 minutes, just take everything offline. So Cortex is a powerful, open source, cheaper alternative to SageMaker, which may soon provide scale to 0, which is a big missing opportunity in almost all of the serverless machine learning solutions out there. So keep an eye on cortex.dev. Check it out. Tell me what you think. Send a comment, send an email. I want to know if anyone has any experience with Cortex. I plan to give it a whirl, and I'll keep you guys posted on what I find. That's pretty much a wrap for this episode. I do want to mention that you can orchestrate your own machine learning architecture. There's solutions out there. There's Kubeflow. So Kubernetes is a declarative orchestration system. So in the same way that a Docker file is a declarative code file for provisioning a server, it sets up the server from end to end. Kubernetes takes it to the next level, and it's the same kind of thing. It's a declarative file that provisions your entire tech stack. So you'd use Kubernetes on AWS or on GCP in the same way you'd use Docker, and it sets up your entire, some instances, some API gateways, some serverless functions, etc., end to end. So, the real big guys, the real DevOps champions of this world, when they're setting up their machine learning architecture, they're probably going to be using something more akin to Kubernetes. And I don't know anything about Kubeflow, but I know that it is a TensorFlow companion to Kubernetes. So it makes deploying machine learning in your architecture more streamlined if you're using Kubernetes. But I don't know much about these orchestration software packages like Kubernetes or Kubeflow. But when I do learn more about these projects, I will do a follow-up episode and fill you guys in. Until then, thanks for listening. See you next time.